Welcome to part 2 of GANs, where I discuss conditional GANs by examining the paper Conditional Generative Adversarial Nets. In the previous part, we observed that the generator G generates data resemble to real images based on a random input. And with the help of a discriminator D, which distinguishes between real and fake data, we aim to improve our generated samples. In this method, we don't have any extra information to control the data produced, as we only have noise as input. The authors of this paper propose that, in addition to random noise, we should add extra useful information to guide the network in producing better results. For example, in the MNIST example, if we pass the digit labels along with the noise to the generator G, this encourages G not to only create more realistic samples, but also match to the specific condition. It is like providing useful information to the G and allowing it to self-supervise generation to output better results. So as you can see in this graph, we had extra information Y to both the generator G and the discriminator D, conditioning the output based on this input. This Y can represent any additional information such as class labels or attributes. This paper presents two applications of this algorithm. The first is for MNIST. As we can see in the picture, for the generator G, we have a 100-dimensional noise and 1 hot encoded digit labels as conditions. We first map both the noise and the labels to a dense layer, then concatenate them and pass the result to another dense layer. Finally, we apply dense layer with the sigmoid activation function to generate a 28 by 28 pixel image for a digit. Next, for the discriminator D, we also pass the labels as useful information. First, we fit them into a max out layer with 240 and 50 units and 5 pieces. In a max out layer, the input is first passed through a dense layer with the specified number of units. The units are then grouped into sets of 5, and then the maximum value is selected from each group. We then concatenate the result and pass it through another max out, and finally a dense layer with a sigmoid activation to output the probability that the image is real or generated. Here's a simple implementation of the algorithm using TensorFlow. For G, we pass both the noise and labels, the output corresponding to a 28 by 28 image. We use a byte size of 64, and for the noise input, we sample a 100-dimensional vector from a normal distribution. This gives us a noise tensor with a shape of 64 by 100. Next, we generate random labels ranging from 0 to 9 for each sample and apply 1 hot encoding, resulting in a tensor of shape 64 by 10, where each row contains a single 1 indicating the label. For the discriminator D, we first implement the max out layer. We determine the number of groups by dividing the total units by the number of pieces. Then we reshape the input into a shape of byte size by pieces by number of groups. After that, we compute the maximum within each group, resulting in output of shape byte size by number of groups. In the function for D, we pass the inputs and labels through max out layers. We concatenate the outputs, apply another max out layer, and finally use a dense unit to represent the probability that the image is real or generated. For example, with real images, we might start with a 64 by 784 matrix representing 64 flattened images. sampled from a normal distribution. As we pass the images through a dense layer, the shape changes to 64 by 240. We then reshape this into 48 groups, each containing 5 units. After taking the maximum from each group, the shape becomes 64 by 48. And this is an image from the paper, shows that each row contains generated outputs conditioned on a single label. In the next application of this method, a combination of image tags and image feature is used to create related tags for each image. Here's an overview of what this network does. For the generator, we pass both noise and image features as conditions, aiming to output tags or words that accurately relate to the given image. For the discriminator D, we use the same image features as input conditions, along with real tags from the dataset and generated tags from the generator. D's role is to determine which tags are relevant, guiding the generator to produce more related tags. For the conditional input, this paper trains a classification convolutional model on the ImageNet dataset, using the output from the last fully connected layer to create a vector representing the image features. To generate text, YFCC dataset is used, which contains the metadata of around 100 million photos and 1 million videos from Flickr. The process begins by pre-processing the tags and descriptions from the dataset. Typically, unnecessary words are removed and the text is broken down into individual words or tokens. These tokens are then used to train a skipgram model. The goal of this model is to predict the surrounding words given a specific word. The final output of the model is a mapping of each word to a vector or embedding that captures the semantic relationships between words. In this paper, the authors trained the model to produce 200-dimensional word embeddings, meaning each word is represented by a vector of 200 numbers. To better understand this process, let's implement a model using TensorFlow. You can skip this part if you prefer. Let's assume we have 10,000 unique words or tokens in our vocabulary, and we want to represent each word using a 200-dimensional vector. For a given target word, we aim to train a model to output high probabilities for words that appear near the target word. For simplicity, let's focus on predicting just the next word after the target word. In the sentence, the dog barks loudly when it sees the cat. We want the model to learn that dog and barks are related. To do this, the embeddings of dog and barks should have a high dot product. This means their vectors should point in similar directions, indicating a strong relationship. Now assume the index of dog is 100 and barks is 900 in our vocabulary. We can represent both the target and context words as one-hot encoded vectors and reshape them to be vectors with 1 row and 10,000 columns. The embedding matrix, which represents each word as a 200-dimensional vector, will have a shape of vocab size by embedding dimension, that is 10,000 by 200. Initially, we start by randomly assigning values to the embedding matrix. Let's implement the training step function to run each epoch and update the embedding matrix. To extract the embedding of our target word, we multiply its one-hot encoded vector by the embedding matrix. This operation activates only the row corresponding to that word. To determine how similar our target word is in the embedding space, we compute the dot product of the target word with every word in our vocabulary, including the context word. This gives us a score for each word, and we aim to maximize the score for the word barks. Next, we utilize the softmax cross-entropy loss function with logits. We pass in dot products and one-hot encoding of our context word. In deep neural networks, logits refer to the raw output values from the last layer before they are transformed into probabilities, usually through a softmax function. We then calculate the gradients and apply them to update our embedding matrix. As we proceed, we observe a decrease in the loss, indicating that our model is learning. We now have a network for generating image features and another for creating word embeddings. The others keep these networks fixed and do not update their weights during the next phase. However, it could be beneficial to explore the effects of updating their weights as well. Next, for the conditional GAN part, the paper utilizes the MIR Flickr dataset and extracts image and tags features using the models mentioned earlier. For training, we pass the image features and random noise through dense layers. Then concatenate the result before feeding them through 2 additional dense layers. This process yields a 200-dimensional output corresponding to an embedding vector for a word. For the discriminator, we feed either real or generated tags along with the image features into dense layers. After combining these inputs, we pass them through a maxed out layer. Finally, we apply a dense layer with a sigmoid activation function to determine whether the tag is related to the image or not. Here is an image from the paper, where in the middle column we have the user tags, and in the right column we have the generated tags by the network. That's it for today's video. See you in the future.